The date today is the 1st of July, 2024. We just concluded our SSAR conference, which we hosted here in Ann Arbor, Michigan. And I'm just going to record the talk that I did so that I can post it and make it available to people online. So my name is Mike. I'm currently a postdoc here at the University of Michigan, and today I'm going to be talking about quantifying Pitviper depth perception from preserved museum specimens. I have my screen up here, so that's what I'll be looking at in the video. First off, I'm going to give a couple really important shout outs. First off, Dr. Allison Davis-Raboski, who I've been working with as a postdoc for the past year. She's spearheading a huge effort to CAT scan snakes from preserved museum specimens as a way to investigate their sensory evolution. Everything that I'm sharing today is just an extension and an offshoot of this larger project. As far as the sensory field calculations that I'll be presenting, I have to give Tyler Hunt full credit for this. This is something that he worked out during his PhD research on croc vision, and he basically came up with a standardized approach for quantifying visual fields, and all I did was recreate this using the CT data. You should definitely check out Tyler if you want to see what his research is all about. It's really cool stuff. Pit vipers are masters of predation, and this is usually attributed to their impressive venom system, which is well known for having prey-specific toxicity. Unsurprisingly, there's a huge bias in the pit viper research in the literature towards venom. However, I would argue that pit vipers are more so masters of perception. After all, the first step in predation is actually perceiving your prey. Traits are optimized through the process of natural selection, and this is in part driven by the coevolution of predator avoidance in prey. Sensory perception must work, so to speak, for a trait like venom to evolve, and I like to illustrate this by saying if you can't find it, you can't kill it, and you can't eat it, since failure at each point has the same fitness outcome, which in this case is just a hungry snake. My talk today is first going to quickly go over how does depth perception actually work in pit vipers. Next, can sensory fields be recovered from preserved museum specimens? And then finally, what is the relative sensory investment for depth perception in pit vipers? Just as a quick background, most of the time when we're talking about depth perception, we're actually focusing on vision. You have a right eye and a left eye, and that gives you your right monocular field, which I'm showing here in red, and your left monocular field, which I'm showing here in blue. But a lot of organisms also have overlap between these two fields, and that binocular overlap is actually what gives you the ability to gauge distance. So that's what I'm showing in the middle in yellow. This ability is what I'm going to be calling depth perception, and it's just how organisms can see how far away something is. And of course, the shape of your head is also really important for this, for defining your blind spots. Basically, all I want to do is measure this, the sensory fields based on all of this information as a way to approximate their ability to have depth perception. So it's actually not that simple in pit vipers because they also have their pits, which are bifocal, just like the eyes. And so this gives them a thermal-based depth perception. Predatory strikes are also linked to fitness because the eyes and the pits are both used for aiming. But the degree of overlap between these two is not really well understood. To try to get at this, I will be modeling sensory fields for both the eyes and the pits in parallel. And then I'm going to overlay the binocular fields together and try to calculate the overlap, which you'll see I'll be referring to that as quadocular overlap. So for this first part, how does depth perception work in pit vipers? We believe that the bifocal ability of both the eyes and the pits is very important, and that's just the right and the left overlap. And of course, the head shape will define where the blind spots are. There's a lot of really amazing snake evolution research that's currently ongoing at the University of Michigan Museum of Zoology. For the people that were able to make the meeting in person, you were exposed to a lot of it, but I've really been blown away by the quality of research that's been going on here. We have a world-class team of scientists. In-house, we have a state-of-the-art CT scanner with a really great dedicated staff who are actually producing and managing that data. And we also currently have the largest preserved snake collection in the world right now as of 2024. And all of this adds up to this being a really great place to make advances in this sort of research. What I've been trying to work on in my little piece of the puzzle is I've been building a framework to basically try to semi-automate the CT data processing. This data is really big and it's computationally intensive to work with, and so as much as I can, I'm trying to automate how we work with it and maximize the quality that we can get from this sort of data. I don't really have time to go over all those details today, so we're just going to jump right in and I'll show you what one of the outputs can be from this sort of work. And so you see this rotating head here, and if you watch the top left corner, you'll see as each eye and each pit is visible, I color-coded them each differently. And what I did is I actually came up with a pixel counting approach as a way to quantify how much of each of those is visible from this stationary camera as the head rotates. And of course, after I do full 360-degree turn, I change the elevation, so the tilt of the head, and then I do it again. And that will effectively completely map out that sensory field for each of these four inputs. And so I'll just let this play for a minute, let it speed up. But the idea with doing this is I'm able to basically create a full sphere around the head. And just to kind of illustrate what that can look like, here you can see the red representing the right eye and the blue representing the left eye. But in the middle, I colored yellow wherever there was overlap between each of these two sides. And again, I did the same thing for the pits, all the colors the same as the video on the top. But in the middle, I just focused on the two yellow fields for the eyes and the pits and where those actually overlap. And so that yellow in the middle is actually what I'll be calling quad ocular overlap, where the binocular fields actually overlap with one another. There is actually parts of both the eye binocular field and the pit binocular field which do not overlap, and I color-coded those white and gray respectively. So can the sensory fields be recovered from preserved museum specimens? And I came up with a scaled pixel counting approach as a standardized way to try to do this. And the sensory overlap proportions were quantified using those spheres, which I standardized. For my preliminary run at this, I looked at 8 Pitviper specimens that we CT scanned, which are all listed here in gray. I looked at proportions calculated from the sensory field sphere projections that I just showed you. And because I only had 8 specimens, I didn't have enough to really talk about species level comparisons. Instead, I wanted to focus on some more broader trends. For the next few slides, I'm going to be summarizing Pitviper investment in depth perception, and this is going to be based on the sensory field proportions that were averaged across all of these samples. And so with the plots that I'll be showing you, there will be error bars, and you can kind of get a sense of the spread of the data. So again, on the bottom, I have all 8 of my specimens that we had CT data for. And on the top, you can see the summary of all of those averaged together. So for the first plot on the left, I'm showing the total coverage of the 100% sphere. In total, we got 85% coverage with the eyes. So that's either right or left or binocular, which is actually a really good visual coverage. Of that 85%, 12% was invested in this binocular overlap. So of the total 85% of the sphere, 12% is being used for depth perception, presumably. If we change our attention now to the pits, we can see a much smaller total coverage, which is expected. The pits are a little bit more focused down and forward compared to the eyes. So 54% total coverage. Of that 54%, surprisingly, we got 12% again. That's not an error. It was 12% for both of these, both the eyes and the pits. So kind of the leading hypothesis that we have right now is maybe there's some optimum at 12% where the ability of snakes to process that information, whether it's from the eyes or the pits, has some optimal level at 12% total overlap. But we don't really know for sure yet. We'll have to do a lot more sampling to really establish this and make sure it holds up. But as of now, with these 8 samples, you can see it's actually pretty tight error bars. So we feel pretty confident this is going to hold up. Now looking at the binocular overlap, so looking at just the eyes, I'll talk more about the pits in a moment. So for the eye, total binocular field, this covers 10% of the total sphere. And of that 10%, 44% is overlapping with the pits in making up that quad ocular investment. And you can actually see that below. Again, I colored it the same as my example slide earlier, with the yellow being the quad ocular overlap, the white being the eye binocular only, so parts of the eye binocular field that do not overlap with the pit binocular field, and then any parts of the pit binocular field that don't overlap, I colored that gray. Moving our attention now to the pits. The total pit binocular field is making up 6% of the total sphere, so a little bit smaller than the eyes. But interestingly, of that 6%, 66% is overlapping with the eye binocular field. So potentially the pit binocular field may have some sort of reliance or functional need to overlap with the eye visual field. Again, this is all just preliminary results, but it at least shows that we can be able to model the sensory fields in a consistent way from these scans. And as we get more samples, it'll be really interesting to see if all of this holds up. So what is the relative sensory investment for depth perception? We compared the average sensory field coverage and overlap proportions with those 8 samples, and we found surprisingly matching 12% binocular field investment, both for the eyes and the pits. And then also the pit binocular field overlaps 66% with the eye binocular field. So here's just a recap of all the things I touched today in this short talk. I'll just quickly go through some acknowledgements. A lot of this was funded by the National Science Foundation. I also want to thank Allison's lab and everyone that's a member. Also Dan Roboski's lab, the University of Michigan Museum and CT lab staff. None of this would have been possible without any of them. And then a bunch of other contributors, and then also some people from Florida State University who I did my PhD with, who also are behind a lot of this preliminary work. I'll just leave up a short list of some key tools that were really important for generating both the results that I got, but also the visualizations that you see here. So thank you for watching, and definitely reach out if you have any questions about what I talked about today. Thanks.